I've been doing some detective work, and what I found rather surprised me. Well, hello once again, and thank you for joining me on this video channel. During the various points I'm going to discuss in this video, I'm going to refer back and actually use this as a means of doing some of the tests and showing you the results. This is the ReigExpert. It's a phenomenal instrument. I'm really amazed at how well it works. And put this close up to the camera. Hopefully the camera can see. It's got a nice screen on it. It's very clear, very easy to read. There's lots of menu items on it, lots of different tools and various things you can do. And I'll put up on the screen now the current price of the HF1, which is the one that covers HF to 35 megahertz. It's probably the most popular one, and it's great value for money. So consider the ReigExpert, but follow me in this video and see what you think. Let's first of all take a look at coax cable loss. It's quite important to us, isn't it? Because it means to say that you're going to lose signal, both on receive and on transmit. Now, all coax cable has a loss, and it gets worse as you go higher in frequency, and it gets worse if you use the cheaper coax cable, because the cheaper coax cable has got a lower spec. But maybe you don't need expensive coax cable, but you do need to know what the loss is. Now, on the outside of the cable, very often it will tell you what the manufacturer's spec is, and you can look up a table in the on the website and find out what the loss is. But of course, you don't actually know whether the cable you've got meets the spec. I mean, who knows where some of this cable comes from? So it's rather important to actually measure the loss. And of course, the losses will increase if you insert a VSWR meter and any other bits and pieces. So rather than just rely on what the manufacturer's tables suggest, it's perhaps more interesting to find out what the actual loss is on the coax cable setup that you're using. Now, our ReigExpert meter has got something on it which measures return loss. And what it means is if we take a length of coax cable and we short the far end, and then we connect the coax cable up to the ReigExpert will send a signal up to the end of the coax, and it will bounce back because it's got a short circuit. Then it will measure the dB loss on that round trip, the trip going up to the end of the cable and back again. But of course, we are only interested in what the loss is on the first part of the journey from the transceiver to the antenna. So we measure the return loss, and then we divide that by 2, and that gives us in dB what the actual loss is on the cable going from your transceiver to your antenna. It's clever, isn't it? Here's the basic setup. We've got the ReigExpert connected to a length of RG58U coax cable, and I've shown below the screen here the length of the coax cable. And if you look at this end, I've shorted out one end of the coax cable with that socket there, and so that cable goes into the ReigExpert, and I've got a DC power lead going to the ReigExpert simply to save battery. If you look at the top right hand corner, you'll see the return loss, and that's 0.88 dB. Ignore the VSWR on the left hand side. There's a reason why it's showing 20:1 and not infinity. We'll come back to that. This measurement is done at 14 megahertz, and if we halve the return loss to find what the actual loss is, we actually end up with 0.44 dB. Now, I should explain that I'm working in feet measurement because most coax loss calculators on the internet show the losses in feet, and that is a tradition going back many years. So I'm working in feet. Now, I had a 25-foot length of coax cable. Most coax losses on the internet or the calculator tables work in 100-foot length. So we have to multiply that by 4. So I've got a 0.44 loss on 25 foot of coax. If I multiply that by 4 to get 100 foot, it means so I've got about 1.7 dB loss on 100 foot of RG58 coax. Now, if you look at a calculator table on the internet, you'll find it should be nearer about 1.4 dB for 100 foot. The reason is, well, basically, I can't vouch for the quality of the coax, but at each end of that coax cable I have got an adapter going from BNC to PL259 because the cable that I got was ready made with BNC connectors on. That means to say that probably those connectors and those converters are adding about 0.3 dB to the overall loss. Now, bear in mind that the loss on coax cable on the tables doesn't take into account any connectors you have on the end of the coax cable. So as soon as you put a connector on the end of a coax cable, you're probably going to you certainly are going to introduce a small amount of loss, and if you put an adapter on it, you'll get even more loss. So bear in mind that as soon as you put connectors and adapters on the ends of cable, you increase the loss on that coax cable. Now I've switched to 28 megahertz and you see that things are a bit more alarming. We've got a return loss of 1.7. If I divide that by 2 to get the one-way tickets to the end of the cable, and then multiply it by 4 to get the measurement for 100 foot, we get approximately 3.4 dB loss. I was expecting about 2 dB. So why have we got an extra 1.4 dB of loss? Well, I think it's the adapters on either end of the cable, plus the moulded BNC connectors on the end of the cable. I've got no idea how they've been connected or terminated because it's shrunk wrapped. But it does highlight the fact that you shouldn't make assumptions on coax cable without actually making some measurements. And we have to thank the ReigExpert for that, because it is really amazing instrument, and I have actually calibrated. I have made sure that it's correctly calibrated. So you can see it's really worth checking coax cable losses, or your particular coax cable losses, with all the connectors on and so forth. And whilst the losses at 20 meters, 40 megahertz are probably not really alarming, they certainly start to stack up when you go higher in frequency. And of course, with the 10 meter band being so popular at the moment, you could be losing quite a bit of power. But just say again, this analyzer really has proved its worth. Now, I thought I'd actually move on to check VSWR meters and coax switches, because there must be some losses there. And I found that on a decent VSWR meter, you get about 0.3 dB insertion loss on 20 meters and on the 10 meter band. So it's not alarming, but it is there, an extra 0.3 dB. And the coax switch I checked, there was 0.1 dB increase in loss on both 20 meters and 10 meters. But you see, all these losses add up. So finally, I decided to connect the 25-foot coax to a coax switch and in turn to a VSWR meter. I used thick cable to connect the switch and the SWR meter together. I used a Watson SWR meter and Watson switch, which are quite high quality, and I found an insertion loss on 10 meters or 28 megahertz of 0.25 dB. So that's not too bad. Now, whilst when you increase your coax cable, you proportionally increase your loss. In other words, if you double your coax length, you double the loss. On things like SWR meters and switches, they are relatively static losses, so they don't have to be multiplied up at all. There will be a slight increase in loss as you go higher and higher in frequency, but at HF you can just accept that those two items added 0.25 dB to whatever length of coax you finally use. Unfortunately, we haven't quite finished with losses yet, because there is one further loss to consider, and that is the loss that's incurred on coax cable when you've got VSWR. Now, if you've got a very low VSWR and you've got very low loss cable, then it's not that significant. But if you've got a 2 dB loss and you've got a VSWR approaching 2 to 1, as you can see, you're approaching a half dB loss, and it gets worse as the SWR rises. And you can see from this chart how it increases when either your cable loss is increased or the VSWR is increased, or both. So we've seen that although you can use a lookup table to calculate what your coax loss is, it doesn't tell you the full story. You've got additional losses from connectors, VSWR meters, coax switches, and of course the extra cable used to connect all together. So what about velocity factor? Can you actually believe what the manufacturers say about the velocity factor? Well, the easy way to do that is to check it out. Now go into the zoom menu, we click on tools and then we click on length, and that takes us to this window, which is quite interesting actually. It's quite powerful. If we go closer in on the screen, if you look, you'll see that the first item says velocity factor, and that's preset at 0.66, and below that's the length. Now, if we assume that the velocity factor of the coax is 0.66, then all we've got to do is connect a length of coax to the input on the analyzer and just press the button, and it will tell us the length of the coax, either in meters or feet, depending on how you've set the analyzer up. Now here's the clever bit. What if you don't know what the velocity factor is? Well, what you do is you measure the length of the coax and you enter the length of the coax in the lower part of the screen where it says length, and then press the return button and it will tell you what the velocity factor is. That's clever, isn't it? So with all this detective work, can we actually believe our SWR readings on our SWR meters? Well, no, you actually can't. Even if you spend a lot of money on a VSWR meter, that meter is not going to tell you the truth. The primary reason for that is that coax losses hide the true VSWR reading on your meter. Let's take a closer look at that. We actually get fake readings on our VSWR meter. We all have fake readings on our VSWR meters, but some of us have a worse reading than others in terms of its accuracy. Let me try and explain what happens. If you've got a VSWR on the antenna at the feed point, say you've got 2:1 VSWR on the antenna at the feed point, we know from what we've just discussed earlier in this video that there's something called return loss. It means to say that the reflected signal, which is the signal that causes the VSWR, reflected signal back down the coax cable, is actually reduced when it arrives at the VSWR meter because of the loss on the coax cable. It means to say that the VSWR reading on your meter is not the true VSWR at the antenna point, and of course the VSWR at the antenna point is the most important thing. So we've got a fake reading. This fake reading actually gets worse as the coax loss increases. So if you've got a really good piece of coax cable with very low loss, the VSWR reading at the meter is not too far removed from the true VSWR. But if on the other hand you've got some significant loss on the coax cable, and that's entirely possible on many installations, then the VSWR reading you get at the meter is going to be a lot better than what it actually is at the antenna feed point. And that's because some of that VSWR information, if you like, has been lost because of the losses in the coax. It's a very crude description, but you get the basic idea. So if you've got a 3 dB loss on your coax cable and all the connectors, it's highly likely that your VSWR you're measuring at the meter is some way removed from what the real VSWR is at the antenna feed point. And I mean, the easiest way to check the VSWR, or the true VSWR, is to connect an antenna analyzer to the feed point of the antenna, or to use a fairly short length of good quality coax back from the feed point to your antenna analyzer, because with good quality coax and a very short length of it, say, I don't know, 10 or 15 feet. Sorry, it's in feet. What would you say? About 5 meters of coax, or something less than that. And probably the reading you'll get is not too far removed. But if you've got a coax run which is, what should we say, 20 meters, 25 meters, then it's highly likely that what you're measuring is not the correct VSWR reading. Nothing you can do about it, that is life. But you need to understand that the SWR reading that you get on your meter is what we call fake reading. It's not true. So let's take some examples, shall we? Here we've got a station with a very low feeder loss, but even so, with a 1.5 VSWR reading on the meter, it's actually about 1.7. With a 2 dB feed line loss, which is entirely possible with a long length of coax or on the higher frequencies, the error starts to become more significant. And when you get to a 3 dB loss, the error really starts to become an issue, because your VSWR is not nearly as low as you may think it to be. And I've now repeated those 3 examples using an indicated VSWR of 2:1 on your station VSWR meter. Now here's something to ponder actually, and I haven't done any experiments with it, but I have noticed that when people have been talking about 9:1 UnUns, they very often say that you need a fairly long length of coax in order to make it work properly. Well, that has never really made sense to me, other than the fact that perhaps you could ponder that the coax cable is acting as a counterpoise. But I just wonder whether it's the coax loss that causes the VSWR to apparently be quite good, when in fact it's not good at all. Let me just put up on the screen a possible scenario. You've put out nearly 100 foot of coax cable because that's what's recommended, and the 9:1 UnUn itself will have a little bit of an insertion loss, so let's say that's 1 dB, so total loss of 4 dB, but it's quite alarming. At a 2:1 VSWR indicated, you've actually got a VSWR at the UnUn of around about 8:1. Now, if you want to have a more in-depth look at these errors on VSWR meters, I'll put a link below this video to a site which I think you'll find quite interesting. Take a look at it, and it'll give you all sorts of examples of various scenarios. And here's another interesting observation you can make. As you get an increased loss on the coax cable that causes the VSWR to be incorrect at the meter, you'll also notice that the bandwidth, the apparent bandwidth of the antenna, improves. So if you do a VSWR curve across the band and you are quite surprised at the bandwidth you've got on this particular antenna, it could be because you've got a significant loss on the coax cable. For example, if at resonance you've got, I don't know, let's say you've got at resonance, you've got a good match, you've got 1.5:1 at the resonant point on the antenna, and you move down the band or up the band, and the VSWR rises to about 3 or 4:1 because you've got a fairly narrow banded antenna. As that VSWR rises, so it has a greater misreading or fake reading at the meter end, because the increase in VSWR actually at the antenna actually increases the error at the VSWR meter. So very often you find that you've got an antenna that has a bandwidth a bit wider than you expected and you're quite happy with it. But in actual fact you haven't really, it's just the meter is indicating that. But the irony of all this, of course, is that with increased loss on the coax cable, you can very often find that your internal antenna tuner will match into the coax cable and deliver power because it sees a lower VSWR than it would if you had lower loss cable. There's a bit of an irony there, isn't there? That if you use lower quality coax cable, you may find that the antenna tuner will match into the antenna system. All it is the fact that the transmitter is delivering power into the system. A bit of it's getting to the antenna, but a lot of it will be lost in heat in the coax cable. You won't be able to feel the heat because it's dissipated over the length of the cable, but nevertheless it's happening. And finally, two other things to remember. First of all, you must remember to use a line isolator just before you measure the VSWR on an analyzer when you're using an antenna, because if you don't use a line isolator, even though you're not transmitted effectively, you will get problems with common mode currents, because that analyzer actually does transmit a low power signal up the coax to make the measurements, and if you don't have a line isolator there, you'll get a further error in your VSWR reading, so don't forget that. The other thing is, you probably may have noticed that your transceiver VSWR meter doesn't quite match your external VSWR meter. The reason for that is two basic things. First of all, the external SWR meter itself inserts a loss, and we've seen it's around about 0.2 or 0.3 of a dB loss, and also the coax cable going back to your transceiver and the connectors. So you've got a further loss that the external SWR meter doesn't see, but the internal one does. So don't be too surprised if the two VSWR meters never actually match each other. So what is your real VSWR? How much power are you losing down your feed line? Not just the coax, but the whole feed line with all the connectors, the SWR meter, the dodgy joins you've got in your coax. Well, the answers to these questions can be obtained by measuring return loss. And one of the simplest ways of measuring return loss that I know of is to use one of the Zoom antenna analyzers. I've used the Zoom A230 because I want one that covers up to 2 meters, but you could use the much cheaper Zoom A-35. Check it out. I'll put a link below this video. Thank you for watching this video, and thank you for your support on this channel. I hope you found it interesting. I found this adventure quite interesting actually, and I'm sure that you will enjoy finding out all those hidden secrets about your own ham radio station. In the meantime, enjoy your ham radio, you take care, and as usual, I look forward to seeing you in the next video. Bye for now.